There we go. Thank you. Thank you for that reminder. Perfect. Awesome. Okay, hopefully we're cooking with gas now. We can move on. Okay. So alternating series test. Okay. If the sum n equals 1 to infinity of -1 to the n minus 1 power b sub n, okay, equals b1 minus b2 plus b3 minus b4 plus b5 minus dot 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 dot, right? It just goes on forever. If this satisfies two conditions, then the series is convergent. Okay, the first condition that it needs to satisfy, okay, if this thing satisfies, okay, number one, that the terms decrease, b sub n plus 1 is always less than or equal to, okay, b sub n plus 1 is always less than or equal to b sub n, okay, for all n. Okay, 2, if that's true, and if the limit as n goes to infinity of b sub n is equal to 0, and if the nth term test, okay, if the nth term goes to 0, okay, if the nth term goes to 0 and the terms are decreasing, then the series is convergent. Now that's not true for all cases. This is only true if they oscillate back and forth. Okay, and let me explain why this is convergent. Okay, just to we'll do an example here in a second. Okay, so then the series is convergent. Okay, then the series is convergent. Okay, so this is called the, let me make this a little bit smaller. This is called the alternating series test. Okay, if that's true, then the series is convergent. Okay. Okay, so let's take a series and see if it's convergent or not. Okay, is the summation n equals 1 to infinity of -1 to the nth power, or sorry, n minus 1 power, to the 1 over n, is this convergent or divergent? Does that converge or diverge? Okay, nice, nice, nice. Okay, so let's look at, let's first look at the nature of this. What's happening here? Well, this would be what? 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5. Now, what did we call 1 over n? The summation as n goes to 1 to infinity 1 over n. This was called the harmonic, right? This was the harmonic series. And did we say that the harmonic series converged or diverged? Converged or diverged? Yeah, we said that it diverged. Yes, it diverges. Okay, it diverges. It diverges because it doesn't go to 0 fast enough. Okay, we keep adding more and more values, and it doesn't go to 0 fast enough. But if it happens to oscillate back and forth, then we say that it does converge. Okay, it does converge. So we could start at 1, and then we would add 1/2, and then we would add 1/3. Or sorry, then we'd add a -1/2, right? This is -1/2. This is 1. Then we would add a 1/3, and then we would go to -1/4, and then we would go add 1/5, right? And we would keep oscillating back and forth, right? right? And we would keep adding and subtracting tiny amounts of value because we're not specifically adding, and we're subtracting as well. This thing will eventually oscillate. Okay, and so the sum will eventually, the limit of this thing will eventually go to 0. The sum of this thing will eventually go to a certain value, and it will converge. This converges. Now, how do we know it converges? Well, we could use the alternating series test to see that it does converge. Okay, so what's the first criteria? The first criteria is that b sub n plus 1 is always less than or equal to b sub n. Okay, so we're saying that 1 over n plus 1 is always less than or equal to 1 over n. Is that true? Well, yeah, isn't 1/2 less than 1? Isn't 1/3 less than, aren't the terms decreasing? The terms are always decreasing. Now, what about the limit? Does the limit as n goes to infinity of 1 over n, does that equal 0? Well, yes, it equals 0. The limit of this thing will go to 0. The terms get closer and closer to 0, and so they just keep bouncing back and forth on the line. And so it satisfies not only the first one, but it satisfies the second one. So by the alternating series test, the series summation n equals 1 to infinity of -1 to the n minus 1 of 1 over n converges. Now, would it have converged if it was not alternating? No. But does it converge because it is alternating? Yes. Okay, and again, there's a reason for that, right? Because before it didn't converge fast enough, right? It didn't converge. We kept adding a bunch of 1/2. Remember when we had those 1/2 that we just kept adding? They were spaced out really far, but we just kept adding another 1/2, and then we would add another 1/2, and then we would add, okay, another 1/2, right? And then we would way far out, right? This would be like we had 16 and 8 and 4, and right, every 1/4 we would just, okay, we would be adding more and more 1/2. Okay, so what happens now though is because we are adding and subtracting, if we look at our partial sums for our alternating series, S2, S3, right? So at first we're at 1, and then we're down to 1/2. And then we want to add, okay, let me explain why we're at 1/2. Because this is 1 minus 1/2, right? Which is 1/2. Okay. And then we're at 1 minus 1/2 plus 1/3. Well, what's 1/3 plus 1/2, right? What's S2 plus the next term? That's S3. 1/2 plus 1/3, wasn't that 5/6? Right? But then S4, what are we going to do now? We're going to subtract off of 1/4. So we add more value, but then we cut it down, right? We quickly cut it down by the next term. So we're always adding, subtracting. We're adding a little bit more and subtracting, and then we're adding a little bit, subtracting, right? So we're not. So it because we're subtracting values, this thing is getting cut down a lot faster. So it starts here, goes here, boom, and after a few terms, we're really close to 0. Okay, because whatever we add, we immediately subtract, okay, the next remaining fraction, and it really cuts this thing down really quickly. Okay, so this thing does converge. It gets really close to 0. The nth term gets really close to 0. Okay, the partial sums get really close to a certain value. Okay, because we're keep adding and subtracting. Okay, number 2 is the summation of n equals 1 to infinity of -1 to n plus 1 of n squared over n squared plus 1. Is this thing convergent? Is it n squared or n cubed? I don't know if it's n cubed. N cubed plus 1. Okay, is this, is blank, I should probably just say, is that convergent? Okay, is that convergent? Okay. So, well, what do we know? Let's write out a few of the terms here and see what's happening. Okay, what does this thing look like? Well, this is going to be -1 to the 1 plus 1 over -1 squared all over -1 cubed plus 1. Is it -1 cubed? No, I'm sorry. This is 1. These are ones, not -1s. I got confused. Okay. Okay, so that's the first term, right? Plus -1 to the 2 plus 1. Okay, all over 2 squared over 2 cubed plus 1. Okay. Okay, plus maybe we'll go out in one more term here. Okay, one more term. So what's the next one going to be like? Okay, that's going to be -1 to the 3 plus 1 times 3 squared over 3 cubed plus 1. Nice. Okay, plus ... Okay, so this thing is going to be, well, what's -1 to the second power? That's just +1. This becomes +1. Okay, maybe I'll write it like this. +1. 1 squared is 1 over 1 plus 1 is 2. So this just becomes 1/2. Okay, this is -1 to the third power. It's an odd power, and so that's a negative. So that's a minus sign. This is going to be 4 over 8 plus 1, which is 9. So 4 over 9. Okay, and then plus, this is going to be a plus because it's -1 to the fourth power, which is positive. 3 squared is 9 over 9 plus, over 27 plus 1, which is 28. The next one would be a minus. It would alternate. It would be a minus. This would be 4 squared, which is 16. All over 4 cubed, which is 64 plus 1, which is 65. And then the next one, so it oscillates back and forth. Okay, so that's what it looks like. Okay, this is what the series looks like. Okay, and so let's see if this satisfies the alternating series test. Okay, number 1, is b sub n plus 1 less than or equal to b sub n? Okay, are all the terms, is this always going to be true? Well, what's b sub n plus 1? Well, that's n plus 1 squared over n plus 1 cubed plus 1. Is that always less than or equal to n squared over n cubed plus 1? Okay, let's see. Let's see what happens here. So, let me multiply this guy out. The top is n squared plus 2n plus 1 over n, I'm going to multiply this out using Pascal's triangle. This is n cubed plus 3n squared plus 3n plus 1 plus 1. Okay. Nice. Is less than or equal to n squared over n cubed plus 1. Cool. So now what I'm going to do is I'm going to cross multiply. Okay, so I'm going to get n squared plus 2n plus 1 times n cubed plus 1 is less than or equal to, n cubed plus 3n squared plus 3n plus 1, plus 2, plus 2 times n squared. Okay, that's good. Some good stuff there. Now let's FOIL this up. Okay, I just want to know, is this true? Is this true? Is this, I want to put a little question mark here. Is this true? Is there, can we prove that, can we show that this is true? Well, let's multiply this out. Let's distribute this all out. And we're going to get n to the 5th plus Okay, what's the next one here? This is going to be 2n to the fourth, right? Plus n to the third. Okay. Okay, and then next is n squared plus 2n plus 1. Is that less than or equal to n to the fifth plus 3n to the fourth plus 3n to the third plus 2n squared? Okay, so let me just check this. Okay, nice. Okay, that's good. Okay, so let's check. Let's check for n equals 1. Okay, let's check for the first term, n equals 1. Does this work? Okay, does this work? So let's plug in 1. 1 plus 2 plus 1 plus 1 plus 2 plus 1. Is that less than or equal to 1 plus 3 plus 3 plus 2? Okay, so let's see what we got here. 1 plus 2 is 3 plus, okay, 1 plus 2 is 3, plus 1 is 4, plus 1 is 5, plus 2 is 7, plus 1 is 8. Okay, is that less than or equal to 1 plus 3 is 4, plus 3 is 7, plus 2 is 9. Okay, so the inequality seems to hold for n equals 1. Let's see. Well, let's do some manipulation here. Let's see if it works for n equals 2. Let me make sure that I did this correctly. Okay, n is n 5 plus 2n plus 4 plus n cubed plus, right? So yeah, this is kind of interesting. So let's solve this thing algebraically real quick. We could go for n equals 2 as well, but we're going to see that it's true. It works for n equals 2. I could plug in n equals 2 here. Okay, but let's just see if we can manipulate this algebraically and see what's going on here. So let's subtract n to the fifth power from both sides. Let's subtract a 2n to the fourth power. Let's subtract a n to the cube power. Let's subtract a n squared. Let's subtract a 2n and subtract a 1. Minus 2n minus 1. Okay. Okay, so that's going to give me 0 is less than or equal to. The n to the fifths are going to cancel out. This becomes n to the fourth, right? And then, so this just might help me and simplify a little bit when I want to work with these. 3n to the n cubed minus n cubed, that's 2n cubed. This is going to be 2n cubed minus n cubed, that's n squared. And then this is minus 2n minus 1. Okay. Okay. So they're saying that this thing is positive. This thing is positive. Huh. Okay. Well, is it positive? Is this always going to be positive, right? Is it always going to be greater than or equal to 0? Is it always going to be positive value? Well, let's think about this for a second, right? Okay. So is 1 plus 2 plus 1 minus 2 minus 1, is that positive? Well, yeah, it is, because isn't everything going to cancel out except for that 1? Isn't that positive? If n equals 1? Yeah, if n equals 1, it works. Checks. It's positive. Okay, so the inequality holds. Okay, what about n equals 2? If n equals 2, then what's going to happen here? I'm going to get 2 to the fourth, which is 16, plus 2 to the third, which is 8 times 2, right? 8 times 2. Okay. which is 16 again, right? Isn't that right? 16 again, plus 2 cubed with 2 squared, which is 4, minus 4 minus 1. Oh, okay. So those, whoops. So everything, those two cancel. The 4 and the minus 4 cancel. And then I get a minus 1 here. So this is really 31. Boom. Okay, so what about n equals 3? If we did n equals 3, well, in a way, can't we see that we're always going to be, these first three terms, aren't they always going to be beating out these last two terms in a way? Because what are we doing? Well, we're multiplying by 2 to whatever the number is. The number is always a positive number. And then we're subtracting by 1. But even the n squared here, wouldn't that beat out the minus 2n for any n greater than 2? So any n greater than 2, right, then isn't n squared greater than 2n? Or we could even say even any n for n greater than or equal to 2, wouldn't that be greater than or equal to 2n? Does that make sense? Like, isn't 9 bigger than 6? Right? Isn't that's always true? That's always true. As long as n's not right. For any n greater than or equal to 2, this is going to be true. Well, why is this true? Well, divide by n. We're saying that n can't be equal to 0. We're not going to start at 0. Then what does that mean? N is greater than or equal to 2. This is always true for n greater than or equal to 2. Well, I just said that. For any n greater than or equal to 2, this is always true. Right? So we know that n equals 1 works. This works for n equals 1. We've also shown that it works for n equals 2. It works for n equals 3. So because any number bigger than 2, this is always going to be true. Okay, that's fine. And what else do we know? Isn't n cubed greater than 1 for any n greater than 1? If n is greater than 1, right? Isn't that true? If n is greater than 1. Does that make sense? If n is greater than 1, isn't n cubed bigger than, going to be bigger than 1? Yes. So wouldn't this term here, which is 2n cubes, wouldn't that always beat out a 1? Absolutely. So this thing will always be positive, which means the inequality all the way back here holds true. And so this is true. Okay, this will always hold. Okay, we've proven it, that it will always be true. This will always be true. Okay, and so criteria number 1 is true. This holds. Check. Okay, yeah, do we have to go through all the work? Yeah, we had to go through all the work to make sure that that holds. What does that mean? That means that my terms are always decreasing. That's what that means. It means my terms are always decreasing. Okay, that means that when I plug in a 1/2, okay, that is greater than a 4/9, which is greater than a 9/28, which is greater than a what was that, 16/65, right? That it's always decreasing. The terms are always getting smaller. Okay, now it's hard to see that with these fractions, but we've proven it. We proved that, look, the inequality always has this to be true. Okay, there's no way that it can't be true. Okay, so now number two is actually a lot easier to prove. Number 2 is the limit as n goes to infinity of n squared over n cubed, over n cubed plus 1. Does that equal 0? Right? That's the question that we want to ask there. Does that equal 0? Does that go to 0? Right? So how can I find the limit of this? Any ideas? You're going to have to do this on your final. So it'd be good to talk about it now. How would I find the limit of this thing? Any ideas? What you got? What you got for me? Can we divide each term by n squared? Absolutely, Gene, we can. Let's call that method 1. You mean by term, you mean the top and the denominator and the numerator? Does that make sense? Okay. Are you dividing by n squared or n cubed? Oh, just n squared. Yeah. Let's just do n squared. So n squared over n squared divided by n cubed plus 1 over n squared. Does that make sense? That's method 1. Okay, and there's a limit here. Don't let me forget the limit as n goes to infinity, right? There's the limit. Nice. Okay, well, what does the top become? And we don't start at 0. This is with the understanding that n cannot equal 0. Okay. So this becomes 1 over what? I'm going to break up the denominator here. This becomes n plus 1 over n squared. Is that right? Okay. Okay. Now what? Now what do you want to do? Now where do you want to go with this? Any more ideas, Gene? Any more ideas from anybody? Should it, okay, Victor says, should it not have been n cubed that we divided by? Okay, well, let's see. Let's see. I mean, that might be a better choice. Let's see. Let's do that. So let's do n cubed, and then let's do n cubed, and then let's do over here. Okay, let's see. Let's see what we got. Okay, so this is 1 over n all over, okay, 1 plus 1 over n cubed. Okay. Okay. So this is going to give me 0 over what? Over 1? Right? Is that good? 0 over 1? Does that make sense? 0, the top is going to go to 0, right? And isn't this going to go to 0? Right? So top goes to 0, bottom goes to 1. 0 divided by 1 is 0. Equals 0. Okay, that works. That works. Yeah, I think that's a good one. What else could we have done? Okay, taking the limit of the denominator, if it goes to infinity, the whole thing will go to 0. Taking the limit of the denominator, if it goes to infinity, the whole thing will be 0. How is the whole thing 0? Isn't 0 plus 1, 1? Frederick? The denominator has a higher power than the numerator. Yes, the denominator has a higher power than the numerator. Yes, so intuitively you would think that yes, eventually this thing's going to go to 0, right? But we have to contend with this extra 1 here that's kind of gumming up the algebraic works, right? So there we go. Martin says, let's just do L'Hopital. Let's get rid of these extra terms and let's see. I mean, yeah, I mean, the thing that you were taught in pre-cal was that, where the heck did that go? Was that if this thing, why does that keep disappearing? It's like disappearing ink. Oh, maybe it's because I create a circle. I don't want to. Oh, okay, is somebody pranking me here? Please. What the heck? Why is it not staying on my screen? Why is it like invisible ink? Stop the insanity here. Oh, I love technology so much. Stop pranking me, please. Got a little tear in my, I got a little tear in my emoji here. Okay, that's me crying. Crying. Those are not happy tears. That's me. No, these are my angry eyes. Okay, there's my angry eyes. Making me angry. Okay, those are my tears. What the heck? Stop. Stop the insanity here. Okay, so yeah, let's just do L'Hopital's rule before. Maybe I need to call an exorcist over and maybe lay hands on my machine and be like, demons out. Demons out. Ah. If anybody knows a good priest, let me know. Okay, n goes to infinity, okay, of n squared over n cubed plus 1. I think this thing is getting jealous. It's like when you break up with a girlfriend and then, you know, that other girlfriend, then you find another girlfriend, and then the girlfriend before is like all like, no, I hope you die and you know, land on 1,000 knives, you know, and you're like, okay, but you don't ever talk to that other one, right? I think that there's some sort of jealousy going on between my machines here. I don't know. It's just my personal theory. You're all like, dude, this guy needs therapy. Like, no, I'm just kidding. Okay, so maybe, who knows? Okay, but anyway, I'm kind of kidding about the whole priest thing, but sort of not. So anyway, whatever. Okay, so the limit as n goes to infinity of n squared over n cubed plus 1. Let's do L'Hopital's rule, right? We got to put the little h there, the little h guy. Boom. Says don't forget the h because this is not an algebraic operation. This is a differential operation. So that's the limit as n goes to infinity of 2n over 3n squared. Okay, so this is again L'Hopital's rule, right? So what's this thing going to be? This thing's going to be, let's do it again, limit as n goes to infinity of 2 over 6n. Okay, now this is an equal sign because it's an algebraic equivalency. So this is the limit of 1 over 3n. Well, what does that thing do? That thing goes to 0. So we're good. We're good. Okay, so by the alternating series test, the series summation n equals 1 to infinity of n squared over n cubed plus 1 converges. So all that work just to get to the fact that this thing, oh, there's a -1, sorry. -1 to the n plus 1 will converge. This converges. Boom. Good. Okay, now would it converge if it wasn't alternating? Probably not. Probably not, because it's equivalent to the harmonic series, really. Okay, it really is. Very close. They're probably like siblings. Okay. Okay. Okay, let's do another one since we're having so much fun. Okay, number 3. Is the series summation n equals 1 to infinity excuse me. Okay, n equals 1 to infinity of -1 to the nth power. That's kind of interesting. It's going to start with a negative. It's kind of interesting. Okay, -1 to the nth power of 3n over 4n minus 1. Is this thing convergent? Is this series convergent? Does it converge? Okay, so let's see what we got here. Okay. Okay, so what do we have here? Okay. Is b sub n plus 1 always less than or equal to b sub n? That's the question. Okay, is b sub n plus 1 always less than or equal to b sub n? Okay. Okay, so what is b sub n? What's b sub n? Well, that's just going to be 3n over 4n minus 1. Right? 3n over 4n minus 1. Okay. That's good. Okay. So let's plug this in. 3 times n plus 1 all over 4 times n plus 1 minus 1. Is that always less than or equal to 3n over 4n minus 1? Okay. Well, let's see. Let's see what happens. Let's simplify this a little bit. So 3n plus 3 all over 4n plus 4 minus 1. Is that less than or equal to 3n over 4n minus 1? Okay, so again, let's simplify a little bit more. 3n plus 3 over 4n plus 3. We got a 3n plus 3 over 4n plus 3. We're spicing it up, making it spicy. Is less than or equal to 3n over 4n minus 1. Okay, so now what do you think we're going to do? Any ideas? Yep, Victor is correct. We're going to cross multiply. Okay, so 3n plus 3 times 4n minus 1. Is that less than or equal to 4n plus 3 times 3n? Okay, cool. Okay, let's see what happens here. Let me foil this out. Foiling. Okay, that's 12n squared. Okay, minus 3n plus 12n minus 3. Okay, is that less than or equal to 12n squared plus 9n? Right? Plus 9n. Is that less than or equal to 12n plus 9n? Okay, and I'm going to put a plus 0 here, just to be cool. Just because I that's how I roll. Okay, that's how me and my homies roll. Okay, 12n squared plus 9n minus 3, is that less than or equal to 12n squared plus 9n plus 0? Okay, let me subtract the 12n squared. Ooh, that's gone. Okay, oh, let's subtract the negative 9. Oh, just look at that. Negative 9. And boom, oh, look at this. Negative 3, is that less than or equal to 0? When is that true? That is always true for any n. Oh, that's nice. And we only have to deal with integer whole number n's anyway. So for any n, okay, so does it hold when n is equal to 1, 2, 3, forever? Yeah, absolutely. So this is true. So what do we know? We know that this is true. True. You, sir, are true. Boom, check. Check into cash. Okay, number 2, let's try the next one. Is the limit as n goes to infinity of, what are we working with here? We're working with 3n over 4n minus 1 of 3n, okay, over 4n minus 1. Okay, is this, what happens here? What happens here? 4n minus 1. Okay, so Okay. So let's see what happens here. Well, what happens here? This thing, well, let's do L'Hopital's rule. Again, let's do L'Hopital's. Limit as n goes to infinity of 3 over 4. That's equal to 3/4, which is not equal to 0. Right? Yeah, it doesn't equal 0. Okay, it does not equal 0. This does not equal 0, which means that this does not converge. Well, does not converge? Do we know that it does not converge? Does not converge? No, we do not know that this does not converge. Okay, we have not proven that this does not converge. Well, yet. We kind of have proven it, but not really. Do we know that this does not converge? No, we just know that that the alternating series test has done what? It has failed me. Okay, it has failed me. It just means that was a bad test. It means that was a bad test. It didn't work. Okay, it did not work. Does that make sense? Okay, it didn't work. Okay, so let's try a different test. Okay, we know that we know that the alternating series test just didn't work. Okay, so let's take another test. Let's take the nth term test. So we can't prove that it converged. Maybe we could prove that it actually diverges. Maybe we could prove that it diverges, right? We can't prove that it converges. We can't do it. The test wasn't powerful enough. But what about the nth term test here? Let's take the limit, -1 to the nth power, right? -1 to the nth power of n goes to infinity, right? Of 3n, okay, 3n over, okay, over 4n minus 1, okay. Interesting, very interesting. Okay, so what does this go to, right? What does this equal? Okay, well, let me think about this for a second. The limit as n goes to infinity of -1 to the nth power 3n over 4n minus 1, right? So we have kind of this numerator over this denominator. Okay, yeah. Let me just play around with this a little bit. I know what happens to this, and I can kind of prove it intuitively. What happens to this? You know, this limit is going to be equal to -1. It's just going to oscillate back and forth. Okay, it's going to be equal to -1 to the nth. Okay, times 3/4. Okay, because we can like focus on this thing. This thing's going to converge to 3/4. Okay, it's going to, right? The series is going to, but then it's going to kind of oscillate back and forth. Okay, it's going to get closer and closer. It's going to go 3/4, and then it's going to go -3/4, and then it's going to get really close to 3/4, and it's going to go really close to -3/4. Right? It's going to kind of bounce back and forth. Does that make sense? It's going to go here, and then here, and then back to -3/4, and then it's going to bounce to 3/4. And then, so does this have a limit? Does this have a limit? If it keeps bouncing back and forth like this, does it actually have a limit? Well, no, it really doesn't have a limit. So the limit here, limit does not exist, right? The limit does not exist. Okay, so if the limit does not exist, then what do we know? then this thing diverges. It diverges. Okay, the nth term test tells me that if the nth term does not go to 0, okay, then it's going to diverge. The nth term has to go to 0 in order for it to, so it's divergent. This series is divergent. How do we prove that it was divergent? By the nth term test. Okay, because what's happening here is this. Okay, so we're starting out, okay, let's look at our first term here. Our first term is going to be negative 3 over 3. Is that right? So that's negative 1. So our first term is negative 1 times 3 times 1 over 4 times 1 minus 3, right? So our first term is going to be negative 3 over, oh, sorry, this is a 1, not a 3. Negative 3 over 3, which is negative 1. Okay, that's our first term. And then what's our next term? Well, this becomes 1 times 3 times 2, which is 6, over, okay, so this thing is, it starts out at 1, it starts out at negative 1, right? But then it's gonna go up to a positive, what is this, 6 over 7, 6 sevenths, is that right? 6 sevenths? Close 6, okay, yeah, 6 sevenths. So this is positive 1. So at 2, it's going to jump back up to 6 sevenths. And then what I'm going to do is I'm going to draw a couple of asymptotes. I'm going to draw a couple of asymptotes here. Where do you think these are going to be? They're going to be at 3/4 and at negative 3/4. Oh, okay. So what's going to happen next? Oh, it's going to jump right here at 3. And then at 4, what's going to happen? Oh, no. It's going to jump down here. I'm sorry. It's not correct. Okay. It's going to, at 3, it's going to jump down here. Okay. And then we're at 4, it's going to jump right here. And then we're at 5, it's going to get really close to this. And then we're at 6, and then it's going to get really close to that. And so what happens here is I keep oscillating back and forth. Right? I keep oscillating back and forth. And so basically what I'm doing is I'm always either adding a 3/4, really something really close to 3/4, or I'm always subtracting something really close to 3/4. And so the sum, right, as s goes to infinity, is either going to be at infinity is going to be at 3/4, or at infinity plus 1 is going to be at 0. You're like, yeah, because I would have subtracted 3/4, right? So it's going to keep oscillating. The sum of the series is going to keep oscillating back and forth. Does that make sense? Because we either add 3/4 or we subtract 3/4. We add 3/4, we subtract. We keep adding and subtracting the same thing, roughly the same thing forever. It has no limit. Why? Because the limit has to be the same from both directions, and it's not. It's not working for me. Okay, so this has no, the limit does not exist, and therefore it diverges. Now, L'Hopital's rule would be kind of hard to do on that one. I don't even know if I would want to try to do that. The limit as n goes to infinity of negative 1 to the nth 3n over 4n minus 1. This one might be a little bit, I might want to call this thing y equals this, and I could plug in some x's if I really wanted to. I might want to call that y, and then I want to take the natural log of y, right? The natural log of y, right? And then try to bring this n down somehow. I don't know. You could mess around with it. Eventually, you might get something, okay, that'll still oscillate back and forth, but it'll converge. This will converge to some number. Maybe it converges to negative 3/4, but it does not converge to 0. Okay, but eventually, yeah, it's just going to go back and forth anyway. So you might be able to mess around with that. I'm not going to waste the time. Okay. Okay, let's talk about the alternating series estimation theorem. Okay, alternating series estimation theorem. Okay, if S equals the sum of -1 to the n minus 1 b sub n, okay, where b sub n, where b sub n is greater than 0, okay, b sub n plus 1 is greater than or equal to b sub n. Okay, so these are, is it greater than or equal to? Where b sub n is greater than 0, okay. So the sum of this thing S is equal to that. Yes, I like what I've done there. Okay, where these are increasing, I think it should be decreasing. Let me check real quick. Otherwise, it wouldn't be, I wouldn't get a sum on this. It would just go on forever. Let me make sure my inequality is correct. I want to make sure, double check. Chapter we're in, chapter 11. I'm absolutely certain. Yeah, it is. It was reversed. Yes, like that does not make sense. Wow, this is what happens when you write notes late at night. You're just like, oh, this should be reversed. Okay, I'm glad I questioned it because Mike, that does not make any sense. Okay, guess. Where this is true, okay, and b sub n plus 1 is less than or equal to b sub n. Latch failed to close. Oh, the latch has failed to close? Why did the latch fail to close? Am I good? Am I good now? Am I latched? Hopefully I'm latched. Okay. I heard you the first time. Let me stop my share for a second. You can, I got that. Thank you very much. Let's go here. Nope, I did not want that. I want this guy. Okay, draw. I want to draw. I want my wavy line to show up. I do not want the lasso. I do not want the eraser. I want this guy. Draw, draw, draw. Draw, draw. Okay, I'm going to exit out. Exit back in. Okay, let's go back out. Oh, maybe this will work this time. What do we think? What do we think? Nope. Still not working. Microsoft. I love Microsoft. Microsoft is awesome. Okay, let's see what we got here. Let's bring it up again. Let's bring it around town. There we go. Come back to me. Come back to, yes, got it. Nice. Now let's see if I can share my screen. And while sharing my screen, it doesn't crash everything. Let's go share screen. Share. Sharing of the screen. Okay, I can erase, I can draw, perfect. Okay, if S, okay, if S is equal to the summation of -1 to the n minus 1 b sub n, okay, where b sub n is greater than 0, okay, so b sub n is greater than 0, and the terms are decreasing, okay, and okay, the limit as n goes to infinity of b sub n is equal to 0, okay, so basically it's saying the alternating series test is satisfied. Okay, if I know the alternating series is satisfied, then what do I know about the sum? What do I know about the sum? If this is true, then what do I know about the sum? I know that the sum is convergent. There is a sum. A sum exists. Okay? Then the sum exists, then S exists. Okay, and the remainder, or the error, we'll call this the error, okay, is equal to the difference between the sum, the true sum, and the partial sum, okay, which is less than or equal to bn plus 1. Oh, that's kind of interesting. So the remainder, which is equal to, okay, the difference between the actual sum and the sum at a specific n is less than or equal to the term evaluate the series evaluated for the next term. Okay, so let's digest that for a second. You're like, what the hell does that mean? It means this. And try to explain this the best that I can. It means that let's do a sum here. Okay, I'm going to do this guy, and I'm going to do this guy. Okay, picture is worth 1,000 words, right? Okay, so what do we know about this series? Well, we know that the series alternates, right? What do we also know? We also know that the terms are getting smaller, right? The terms are getting smaller. Okay. So I'm always adding a value, and then I'm subtracting the next value. And then I'm adding a value, and I'm subtracting the next value. I'm adding a value, and I'm subtracting the next value. And I'm adding a value, and I'm subtracting the next value, right? So let's make this the harmonic, just for kicks and giggles, okay? Let's make this the harmonic. Let's let b sub n equal 1 over n, right? And what do we know about the harmonic itself? It diverges. But what do we know about the alternating series harmonic? It converges, right? It converges. It starts at 1, but then it goes down to -1/2, and then it goes up to 1/3, and then it goes down to -1/4, and then it goes up to 1/5, and then it goes down to -1/6, and then it goes up to 1/7, and then it goes down to -1/8, right? And then it goes up to, what does it go up to? It goes up to, 1/9, right? 1/9. Okay, so here's the deal. Okay, let's think about this. Okay, so let's look at the partial sums real quick. Okay, we know that the series okay, negative 1 to the n plus 1 of 1 over n is equal to this, right? N equals 1 to infinity is equal to 1 over 1, right? So that's 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 minus 1/8 plus 1/9. And it goes on forever, right? Okay. Let's look at the partial sums of this. Let's just start adding these up. S1 is 1, right? What's S2? S2. S2 is equal to 1/2. What's S3? S3 is equal to 1/2 plus 1/3, right? Okay, 1/2 plus 1/3, which is 5/6, I believe. Okay, and I'm gonna grab my calculator here. I hopefully this doesn't crash my system again. I'm getting a new system on Wednesday that has 4 times the amount of RAM and about 10 times the amount of hard space. And what else does it have? It has 4 times the amount of RAM. It has the 10th generation i7 chip in it, which supposedly is the latest and greatest. I went out and I contacted Dell. Cancel. And I was like, give me something that's going to work. Oh, yes, it is an XPS. How'd you know? Let's go. Yeah, it is. It's an XPS because I was like, I didn't get. I was on the phone for 3 hours buying a computer. I did this at like 1 o'clock in the morning, from 10 o'clock at night to 1 o'clock in the morning, right? So I could have gone higher to do like an Alienware or something like that, but I didn't need it, and I didn't need a dedicated graphics card, but I can upgrade if I want to. So I call up Dell and I'm like, here's my deal, okay? I got to teach. You got to let me teach. She's like, okay, what do you do for a living? I'm like, okay, I'm a professor, right? And she's like, okay, so I got to teach. I got to teach from home. And she's like, and the lady's like, I said, don't lie to me. If you lie to me, you're done. You're not going to sell me a computer tonight. So be completely honest with me. And she's like, I'm an honest person. You know, I'm like, okay, what city are you in? And she's like, I'm from Dubai, India. I'm like, okay, right? Because they're all in India at 12 o'clock at night, right? Because it's a 12-hour difference. So I'm like, okay. So I was like, what's your first name? She says, it's Honey. I'm like, are you serious? So I'm supposed to say, could you get me a computer, honey? And she's like, yes, that's fine. I'm like, okay, because over here in America, it's a term of endearment. I'm like, oh yeah, that's fine. So I'm just calling her honey for 3 hours straight. And so I'm going through all the specs on every single thing with her. And I got an educator discount. I got everything. Boom, 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 boom. I got my machine. It's an i7 10th generation, 16 gig of RAM, 1 terabyte of hard drive. I can upgrade to a solid state hard drive if I wanted to. I could put in an NVIDIA video card, right? So just ignore me and Barappa here. What's the name you go by, Barappa? Barappa, is it Fa? Just call me Mike. There you go. Okay, so yeah, exactly. Okay, so me and Mike are just gonna geek out for a second here. Okay, so I call her up. I'm saying, you got to be honest with me. As soon as you lie to me, I'm gone. I tell that to car salesmen too. I'm like, as soon as I find a lie in anything that you tell me, I'm done. We're done. I'm leaving. And she was completely honest with me through the whole thing. She's like, okay, we're gonna get you this process, so we're gonna get you this price, blah 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 blah, right? So I got a brand new 24-inch monitor, top of the line. It's a premier monitor for like under 200 bucks. I got an XPS with top of the line, right, for under $900. So So I walked out of there for about $1,000, and supposedly it's going to be a super fast machine. So yeah, exactly, right? So I was basically, I was like, and I kept asking her, right? Yeah. So right, exactly, exactly. So who is sharing their microphone here? Let me let me get rid of you. Let me go to participants. Okay. And then Frederick, turn off your dang mic. There you go. Okay. So yeah, yeah, with the student discount, right? So but I was like, no, you gotta get me a good deal here, right? And they're like, oh, well, you get a 2% discount on this, blah blah blah. And I said, okay, well, I have a Premier account through Dell because I buy all my computers through them. So I'm like, dude, you're gonna treat me well here or what? So she's like, okay, I'll put you on hold. And then went through all the specs. It took a long time because I was looking at two different machines. I was like, I'm gonna go through all the specs, right? Blah 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 blah. And so and I said, okay, what's the best that you can do? Right? What's the best you can do for me? And she's like, oh, well, we could get you for like $930. We get you this top tier, blah, 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 right? Blah, blah, blah. And I was like, okay, no. I said, you need to be honest with me, honey. You need to be honest with me. And she says, okay, you know what? I'm going to leave for about 10 minutes and I'm going to go talk to my department manager and we're going to see what we can do for you. I said, look, you got to get me a good machine. So then she comes back and she says, okay, $879 is the bare bones that we can go on this machine. I'm like, okay, honey, is that a good deal? And she kept saying, yes, Jason, this is a very good deal. I'm like, and I asked her, I said, is this a machine that you would want yourself? And she says, yes, this is a machine I would want to have on Christmas morning. I'm like, okay. I'm like, wrap it up. So what I ended up doing was getting a 15% discount on the machine itself and the bundle. So it was just like, yeah, I was like, I did a 6% discount. I financed it for 12 months free interest for a year. So all I'm going to do is basically pay $100 a month and borrow their money for a year. Big deal. Basically, it's what I would be paying in gas if I was. I figure it's just offsetting, my gas money. So I got this sweet machine coming on Wednesday, and so hopefully I won't have to deal with any of these more crashes. I'll have a fast video card that it has Bluetooth, Wi-Fi. It's maxed out. I'm like, give me something. Now I could have gone with an i9, right? An i9 but it was like an extra $1,000. I was like, I'm not paying an extra $1,000 for a little bit more speed. Right, exactly. Right. It's like it's just like this. They relabeled and like, oh, it's a new, and I'm like, no, it's not. Yeah, exactly. I didn't fall for that either. I'm like, no, just give me the 10th generation i7, boom, and we're good. So I got that coming soon. Now I know that doesn't really help you guys out, but it'll help me out because I am stuck at home behind this screen for an entire year. I do not get to go back into the classroom for at least 1 year. Yeah, but that's what happens when you work for the state of California. But anyway, we won't get into that. Okay, so I'm gonna have a machine that works. If I have to pull my hair out over technology over the next 12 months, that's not gonna make me a happy camper. And so I'm gonna have a machine that works. So anyway, thank you for letting me geek out with my friend Mike here. Okay, so boom. So I basically got everything for a little over $1,000. So brand new 24 LCD projection monitor. The cables are all coming. I got a wireless keyboard and mouse to go with it. The whole package for a little over $1,000. So it's a good deal. Good deal. So next time you're shopping for a computer or a car, just take me along and I'll get you good deals. Okay. Do not, I scare them. I'm like, as soon as there's a logical fallacy in anything you tell me, we're done. They're like, okay, I can't lie to this guy. Okay, there you go. Okay, anyway, back to the series that we're dealing with. Okay, the alternating series here, right? Okay, so we're going down and up, down and up, down and up, right? So what would S4 be? What would S4 be? Boom. Okay. Okay, and anyway, it's a lot of money. It's a lot of money. I mean, like, it's $1,000. That's a lot of money to me. So I want to make sure that I'm getting the right thing. Because I mean, that's a lot of food money right there. Okay, anyway, I digress. Okay, so 7/12. Oh, thank you, Susan. She's like, let's get back on track. Exactly. Is it 7/12? Again, oh, the reason I said that was because I was going to bring up my calculator. And I was like, I don't want to crash my system because, right? I don't want to activate my license. Okay. So let's see what we got here. Okay. Okay, so what we're doing. Let's do this. Let's do this. And we were going to go 1 clear. So we were going to go 1 plus 1/2. Come on, move this thing out of the way. 1/2, or 1 minus, sorry. Thank you. 1 minus 1/2. Okay. Okay. And if I really want to do that, I can change this to a fraction, right? So, okay, so 1/2 plus 1/3. Okay, and then again, change that to a fraction. That should be 5/6, right? And then what we do, minus 1 plus 1 minus 1/4. Yep, 1/4. Okay, is that, and then math, fracket. Okay, 7/12, perfect, 7/12. Let's go back here, that's 7/12. Okay, and then S5, okay. S5 is going to be a plus 1/5, is that right? Plus 1/5. Okay, and that's a 47/60th. 47/60th. Okay. So, right? Okay. So, yeah. Okay. Yeah. Okay, 47/60th. Let's see if I got anything else going on here. Okay, whatever. Okay. Let's clear that. Okay, 47/60th. 47/60th. So this is 0.5. This is 0.833. This is this, it kind of goes, up and then it goes down. Here it went down, right? And then went up a little bit. And now it's going to go down, right? So down. So 7/12, right? 7/12 is what? What was 7/12? Maybe I should just do the decimal. Oh, it was 0.5833, right? 0.5833. So 0.5833. And then what's it going to do? It's going to go up a little bit, right? To 47/60th. Okay, and I'm going to hit enter on that one. And it's going to tell me what the, oh, it's not. Okay, so let's go to the math key and then go to decimal. And then we're going to say, boom, 0.783333 forever. Okay, 0.7833, right? So we're honing in on something, right? So so here, what did we do? We subtracted 1/2. Here we added 5, or we added 1/3. And so so that's saying that it is approaching some sort of value, right? It's approaching some sort of value, right? The sum, I'm talking about the partial sums, right? We start at 1, and then where do we go? We went down to 1/2. And then we went up to 5, 6, which is pretty close to 1. We went up to 5, 6. And then we went down to, which is 0.833, right? So this is 1. Okay, this is S sub n. Or sorry, this is n, and this is S sub n. It's not A sub n anymore. It's S sub n. This is the graph of the partial sums. So it went 1, and then it went 1/2, right? And then we went to 0.833, and then we went down to 0.5, right? 0.583. Okay, and then where do we go? 0.7. And then we'll probably go down a little bit more, and a little bit more, and a little bit more, and we're eventually going to hone in. And the sum is going to converge to some number, right? I don't necessarily know what that number is, but it's going to converge, okay? Now, if I kept doing this, okay, if I went out, kept doing this, well, there would be a certain S value that this thing would converge to. We know it's convergent, and it's going to converge to a certain S value. Okay, I don't really know what that value is. I could probably figure it out using a calculator if I really wanted to. Keep adding and subtracting small values and seeing what, what's the error on this thing. And it's going to get closer and closer to some value. Okay, and so I don't even know if I could do that easily on the calculator or not. I don't think so. Let me see what we got here. So we're going to take this guy, and eventually I should get, right, so I want this guy minus the next thing, right? So it was minus 1/6. This guy minus 1/6 actually might be pretty easy to kind of hone in on something. So that's 0.6, right? And then it's going to go up, up 1/7. I'm just going to work with the decimals, and then it goes up to there, minus 1/8. Eventually, this should hone in on something. It may take a little while because of the way that this function operates. Then plus 1/9, right? And so, I mean, it's really hovering right around that 0.7 mark. I don't know what it is, but, and then plus 1/10. But you can see, right, that it's really gonna. Oh no, not plus 1/10. Sorry, minus 1/10. I got a minus 2/10 this time. Minus 2/10 because I added too much there. Okay, boom, and then plus 1/11. Okay, and then you could write a computer program that'll do this for you, and then minus 1/12, right? And so it's honing in, it's honing in. So I'm going to say that it's somewhere around maybe 0.7. I don't know. Again, let me think. I don't know how. I don't know. I don't know how I would do that. Increments of 1, blah, blah, blah. I was thinking if I could write a function that would generate these values, but I don't think I can real easily. Because then I could just plug that function in, and then the calculator would generate for me. But you can see that they're honing around, right? So at 1/9, where were we? Where were we at 1/9? Let's go back to 1/9 here. Okay, let's compare 1/9. Okay, and minus 1/10. So at 1/9, we're at 0.745. 0.745. So at S sub 9. Okay. Oh, come on. Work for me, please. There we go. Okay, at S sub 9, we were at 0.75. What we're at? 0.745. Or we'll say 0.7. Okay, can you at that point, divide by 2 to get the average, to get the estimate? No, because you don't necessarily know exactly like where, like if it's going to eventually go higher or lower. You know what I'm saying? We can't really make that prediction. It's not going to be, it's not symmetric. Does that make sense? Because we keep adding and subtracting different fractional units. Yeah, it's not symmetric on both sides, so we can't just, you know, split the difference. We can get a rough idea. We can eventually get this in within boundaries, right? The farther we go, the smaller our boundaries are on what the value actually, what the sum could actually become. Okay, it'll oscillate a little bit eventually. If I go out to 10,000 you know, 10,000 terms, this thing's gonna get very close to some value. And that's what I want. I want to know what's the error. What's the boundary on the error, right? That's the whole thing is what's the boundary on the error. And so, you know, if we did S10, right, what was the next one in line? S10 was, it's not the next one, because that was an error. It's 0.6456, right? 0.64, oh, look at that, isn't that interesting? It's a difference of 0.1 there. 0.7456, and then I guess that makes sense because oh yeah, of course there's the difference of 0.1 because we subtracted by 1/10. Well, duh, that is. Okay, 0.7563, was that right? Come on, go back. There you go. 0.74563. 0.74563. 0.74563. And this is 0.64563. There we go. Boom. Okay. So we know that we have what? We have an error bound of what? We have an error bound of 0.1 here. Does that make sense? Does that make sense that there's an error bound of 0.1? Right? Because if S sub 9, right? Because what's going to happen if S sub 9 is 0.74563 and S sub 10 is 0.64563. I just wrote the exact same thing twice. How can I explain this? Okay, so let me put this in like this, 0.74563, right? And then I would have subtracted, right? I would have subtracted 1/10, right? To get the next one. So let me write it like this as an interval, right? So I know that at some point, 0.64563, right? And 0.74563, come on, write for me. 745 4 745 Are you kidding me? Let me write. 4 5. Okay, and stop my sharing. I'm going to close out of the application. Okay, where did the application crash? Where the heck is the, oh no, there it is. Close out of this guy. Okay. Try to go back in. Man, that's a lot of emails. Okay, back into the application. There we go. That's still not working. Okay, let's try again. Okay. It's like the system gets overloaded and it's like, nope, I'm going to stop working for you. And then it doesn't want to behave. Like, okay. Okay. Okay, so 7-4. Is it me that keeps doing this? So 7-4, 5-6-3. I can't write again. It's not my pen, is it? Nope, not my pen. Let's try it one more time. Let's close out the application. Let's go. Don't want you. I want the other guy. I might just say screw it and open up an Adobe document and write on that. I just need something to write on. That's all I care about. I don't need to save what I write on. I just need to write on something. Or maybe whiteboard. Let's see what happens when I do Microsoft Whiteboard. Will this allow me to write and continue to write? Okay. I don't know if this is what I wrote. Like if that's what I wrote or if this is something that one of my children wrote. Okay, what does it say? It says, hello, my name is Jason, and I love to do drawings of funny little creatures. That is amazing right now. Cool. So cool, huh? Okay. That's great. Thank you so much. Let's erase that. I don't know where that came from. That's good. Okay. Whoa. Okay. So, yeah. Spooky. There you go. Yeah. Okay. I like to do drawings of little creatures, I guess. I didn't realize that. Okay. So let's see if this allows me to draw on it. It says it's a whiteboard. So let's see if it's a whiteboard. Okay. So we had S. Ooh, that's nice. S sub 9. Oh my gosh. Are you kidding me? S sub, can you guys see what I'm seeing here? S sub 9. S sub 9. Okay. Okay. S, that's not working. It's not making, you know what? I'm actually going to try the other one here. Yeah. I'm going to try to cheat. I'm going to try to cheat. Let's do a workaround. This is how we work with these guys. You got to have plan A, B, C, and D. Okay, so where's my file? My file is on my computer. Where is it? I'm going to browse. Where is it? It's in my desktop. It's in my Dropbox. Let me use a mouse. It'll be faster that way. Okay, so where is it? It's in my Dropbox. Thank you very much. Where is it? It's Cerritos College, and it's reference. Okay, here's the reference. I want to go down to blank document. Okay, and this should give me enough space to write on. Can I write on this? Is it going to allow me to write? Is it going to allow me to write? I don't know. I don't want, nope, I don't want, close that. Okay, can I edit it? Good, preferences, commenting. No, that's, you can use the pen directly, Marco. Okay, perfect. Awesome. Nice. Thank you very much. Can I, is this going to allow me to work? Nope, hell no. Okay, I'm going to reboot my system. I'll be right back. Why don't we take a water break or like a deep breath, cleansing breath break? Because that's exactly what I'm going to do before I throw my computer out my bedroom window. So anyway, okay. So we're going to take a 10-minute cleansing break and I'll be right back. Okay, this is a water checkpoint. Okay, and we're gonna do that. Bye. See you later. In a minute. I'll be back in a minute. Don't go anywhere.